Welcome back, ladies and gentlemen. In this video, we'll be talking about electricity. To mention right off the hop are a couple of good resources for you to check out, that being the Engineering Mindset, which is a YouTube channel and a website, and also an applet called FET DC Circuits, which I'll flip over to throughout this video lesson. Okay, so what we will cover with electricity is on your screen. In this video, we'll talk about the basics of electricity, static electricity, and Ohm's law. Our homework assignment will be from the Ohm's law portion of this lesson, where we're combining voltage, current, and resistance and talking about the relationship between those three. In later lessons, we'll talk about electricity in our homes, electric power and energy. Then we'll look at series and parallel circuits and apply Kirchhoff's laws to solving circuits. Okay, just a little bit of theory. Everything that has mass and takes up space we define as matter. There are four states of matter: solid, liquid, gas, and plasma. There's a plasma ball on your screen, which is our fourth state of matter, which we don't talk about a whole lot, but it is by far the most common form of matter in our universe. Scientists believe that it makes up about 99% of the visible universe. And really, plasma is just kind of a subset of gas, where we take atoms and separate the electrons and the nuclei of atoms. Okay, all matter is made up of elements. We've all seen this table before. Elements cannot be broken down into simpler substances, and elements, as we know, are made up of atoms. And so inside of atoms, we have three main subatomic particles. We have protons and neutrons that make up the middle of an atom, or the nucleus. And then we have electrons that rotate in or exist in shells outside of the nucleus. Here is a table that summarizes those three particles, the charge on each, and the mass and the location of each. The one that we are going to be primarily considering and talking about is the electron, because electrons are light and easy to move. They are the things that are moving around. So if you think about the inside of atoms, you can think of the big sumo wrestler being the nucleus, and this little sumo wrestler being an electron. And electrons are really what we're talking about with electricity. It's the movement and behavior of electrons. Okay, so we will talk a little bit about static electricity and then move into current electricity. Static electricity is really just a stationary charge that is built up on the surface of a material. It's caused by friction, and it just passes electrons from one surface to another. There's a good TED Ed video on static electricity you can go and check out if you like. It's under 4 minutes. It goes into a little more detail about what causes static electricity and how charges are built up. Okay, just for interest, there's this thing out there called the triboelectric series that just has a look at the willingness of a material to either gain or give off electrons. Okay, regular uses for us in society of static electricity is saran wrap, spray painting on cars, and even lightning rods that put on buildings to divert all of that charge that gets built up in clouds. Okay, the whole reason that saran wrap works, or the paint on cars works, is because of the laws of static charges, which is really just that opposite charges attract. Okay, so things that are negatively charged will stick to things that are positively charged. And then also like charges repel. So on your screen, you'll see what you're looking at is the electric field lines. You go into more detail in this in Physics 12. But the whole idea that like charges repel is why we have current electricity, or moving electrons in a circuit. Okay, so in Physics 12, you'll also look at a law called Coulomb's law. Coulomb's law is an inverse square law, very similar to our universal law of gravitation. So, and as we talked about with gravitation, as 2 point charges, or in our case with gravity, if we move two masses further apart, the force of attraction decreases by an inverse square factor. So if you double the distance, you decrease the amount of force between them by a factor of 4. So again, Coulomb's law, it's something that you'll look at in greater detail in Physics 12. Okay, so another couple of things that you can Google if you're interested to play around with static electricity. You can Google FET John-Tree voltage or FET balloons and have a look at how electrons move around a couple different surfaces. Okay, so the demos that we would have done in class, or you can play around with at home, is just some. You can rub your hair in a balloon, and we all have done that before, and try to stick a balloon to a wall or push a pop can. Static electricity. Okay, so the 3 key points that we'll just keep in mind with this is that, hey, static electricity, it's just a buildup of electrons in one place. It's caused by friction. Okay, electrons repel with an electric force, and repelling electrons is the whole reason why we have current or moving electricity. Okay. Okay, so next, with current electricity, this applet on the screen just shows a battery. So the circuit symbol for a battery is on the screen. We use that quite a bit. We're going to talk about how electrons flow around conductors. So conductors versus insulators. Conductors allow electrons to flow easily. Next is we'll talk about is electron flow versus conventional current. So I'm just going to mention this here. Electron flow versus conventional current historically dates back to Benjamin Franklin, who originally thought that electrons or charges move around from the positive terminal of a battery. So conventional current, we call it convention because that was the convention for a long time when Ben Franklin back in the day started doing a lot of science around electricity. And then what we've realized or gained more insight on is that, in fact, electrons are actually moving from the negative terminal of a battery and in the direction that is shown on your screen. Just to realize that they are different in different directions, but they're really talking about the same thing, and that's electrons flowing around a loop. Okay, we'll talk about Ohm's law. We'll define current, voltage, and resistance and talk about that mathematical relationship between them. Okay, and some circuit symbols. Circuit symbols we'll talk about as we go. The first one, a big one that we'll use quite a bit, is battery. There is the symbol for, this is for a light bulb. Okay, and then we'll talk about circuit symbols for some different things as we go. Okay, so first, a little bit of a recap from Science 9. Insulators, those are things that do not allow electrons to flow, things like plastic, rubber, and glass. So if you look up at Hydro Tower and you see a big thing that looks like this, that's a glass object that is designed to keep charges separated between that metal tower and the electricity that's traveling along the lines. Okay, conductors, on the other hand, those are materials that allow electrons to flow. Things like copper. We use, there's copper in most buildings to carry our electricity around. Okay, so talking about current, then voltage, then resistance. Current is just the amount of charge, which we talk about in coulombs, passing a point per second. Okay, so the formula for current is I is Q over T. I is the symbol for current, Q is the symbol for the amount of charge, and T is time. Okay, our units for current are the ampere, and 1 ampere is really just equal to 1 coulomb passing a point in 1 second. Okay, the tool that we use to measure current is the ammeter. We align that in series. We'll talk more about that in the next slide. Okay, and electricity, we often use a water analogy to talk about electricity, and you can think about the amount of water flowing in a pipe is analogous to the amount of current flowing in a circuit. So here, if you have a skinny pipe, you're going to have less current. If you have a bigger pipe, you're going to have more current or more flow of water. Okay, so measuring current. So with current, this is just a key point that we must run electrons through an ammeter to measure current. So Our circuit diagram that is going to be very familiar to us. There are 4 things on the circuit diagram to point out. This A in a circle is an ammeter. An ammeter measures current. This V in a circle is a voltmeter. Voltmeter is something that measures voltage. And then R is our symbol for resistance. And the circuit symbol for resistance is on your screen. It's just a squiggly line. Okay, so I'm going to flip over to the PhET applet and just have a look. I've set up a simple circuit, very similar to what's on the previous screen. I can open and close a switch and see, hey, if I have an open switch, then electrons can't flow. But if I close that switch and give those electrons a conductive path, then electrons will flow around the circuit. So measuring current, I've pulled out a couple of things over here for being the voltmeter and an ammeter. Okay, so for measuring current, I need to actually break this circuit and run current through this circuit so that I can measure it. So current, or the ammeter, is really just measuring how many electrons are passing through this meter in a certain amount of time. Okay, with this applet, I can go and click on different things like the battery and go and pump up more voltage through this thing, and we'll see what happens to the current, right? More voltage, more current. More current, more light. Okay, so this is an applet that you can play around with to set up some different circuits. We'll come back to this in a couple slides when we're talking about voltage. Okay, so here's an example where we'll actually apply some numbers. So if you have 4.5 amps flowing through a wire, how much charge passes in 38 seconds? Well, our formula on our formula sheet is I is equal to Q over T, or current is equal to the amount of charge divided by time. If we rearrange that formula to figure out how much charge, or Q, passes in 38 seconds, it'll be current times time. Okay, so here we'll plug and chug our numbers. 4.5 amps is the same as 4.5 coulombs every second. For 38 seconds, we end up with 171 coulombs. Okay, so the next thing is just a key, just a point of note. If you look on the back of your formula sheet, you will see the elementary charge, which is E, is equal to 1.6 times 10 to the negative 19. This is called the elementary charge, and it's used quite a bit in Physics 12 to solve problems. You can also then, knowing the charge on an individual electron, we can know how many electrons are actually flowing in 38 seconds. 171 coulombs, there's how many electrons are flowing, and I don't even know how to say that number. It's so big. Okay, so just a key point, the elementary charge is a constant that we use in physics. You'll use that more in Physics 12. Okay, next, voltage. We also call voltage a potential difference. Okay, if we define voltage, it's defined as the electric potential energy, or EPE, how much potential energy per charge. Okay, it's also, we talk about it as the pushing force on the electrons in a circuit. Our units are the volt. 1 volt is equal to 1 joule for every coulomb of charge. Okay, we measure that with a voltmeter. We'll measure it in parallel. Come back and mention that a little more on the next slide. So voltage, again, if we go back to our water analogy, the height of the water represents the amount of voltage. This is similar to gravitational potential energy, where if we drop a ball off of a 1 meter height versus a 10 meter height, we know that if we drop a ball from a greater height, it is going to have more gravitational potential energy. Well, if you give electrons, each charge, more potential energy, you are giving it more voltage. Okay, so how we set up our voltmeter, so voltage, again, is going to measure the difference in electric potential energy. So we need to arrange our voltmeter on either side of a gain or a loss in electric potential energy. So a gain in electric potential energy, you hear me talk about a voltage gain, we're talking about electrons going through a battery. If we hear me talking about a voltage loss, we're talking about electrons going through a resistor or an electric load. Okay, so I'll flip over to the FET and just show you what that looks like on here. So our voltmeter, we just have to make sure that we are arranging our these terminals on either side of a gain or a loss. If I arrange them looking at how much energy each of these electrons has gained or lost as it goes through just the wire, you see our voltage is zero. There is no difference in electric potential energy in these electrons from one spot to another. However, if I move these terminals over to the battery, I can put the voltmeter on this battery and say, oh, okay, well, the voltage across the battery, our voltage gain in this circuit is 27.5 volts. Okay, so then I can also arrange this voltmeter for voltage going across a light bulb. So here I have it set up so that my voltage or my electrons coming into the battery are on the red terminal. So I'll put the electrons going into the light bulb with the red terminal as well. And if I put my black terminal on the other side of the light bulb, we see that the voltage is the same, just opposite in sign. So our voltage drop or our voltage loss through the light bulb is equal to the voltage gain through the battery. And this is just a little precursor to something we'll talk about later, being Kirchhoff's rules. And that is the idea that the voltage gain around a loop, so in our case, if we had 27.5 volts, I'm just arranging another voltmeter across our battery, 27.5 volts. I know, or we'll talk about this in greater detail, I know that this voltmeter will read negative 27.5 volts. Okay, a little precursor, Kirchhoff's loop rule is that the voltage gains around a loop are equal to a voltage, or our voltage losses. So in a loop would just be, if I think like an electron, just going around this loop back to where I started. Okay. Okay, so if you want to look at how batteries work in more detail, have a Google, or you can Google TED-Ed, how batteries work. It's another 4-minute video just on a little more detail on how those things work. The basics of every battery are that they convert chemical energy into electrical energy. There are 3 parts to all batteries: the positive, negative, which are cathode and anode, and there is also an acid that helps to dissociate electrons between 2 metals, which are 2 metals in the battery are positive and negative terminals. Okay, our last physical quantity to talk about in circuits or electricity is resistance. Resistance just limits current flow. Okay, the units are ohms with the symbol omega. That's a Greek letter omega. It's measured with an ohm meter. Okay, and examples are light bulb heaters, anything you plug into the wall. Okay, and I'll also talk about resistance. You'll also hear me talk about electric loads. These things, light bulbs, heaters, these are also known as electric loads. However, and these things up here are actual resistors that are found in all electronic components. It's one of our most common electronic components that we have in our devices. The main symbol that we use to talk about all those things, though, is just the thing that's circled. That's just a squiggly line representing a resistor or an object that is limiting the current flow through an object. Okay, so then let's talk about some tools that we use to measure these things. Here are the analog versions of how we would measure both current and voltage in a circuit. Okay, here is a digital multimeter. This is a pretty common tool that electricians use, or DIYers around the house use to analyze circuits. This thing will let you know how much direct current voltage, alternating current voltage. It will tell you the amount of current that's running through something. You can measure the amount of resistance in resistors. You can check for continuity in a circuit. This digital multimeter is really a handy tool for measuring lots of things within circuits. Okay, so just to recap, recap is just our physical properties, just what they are, units that we use, and then how we measure those things. Okay, so next up, we'll talk about how these three things are related. Ohm's law is V is equal to IR. Okay, so we can also rearrange that formula to find different quantities. So if we're looking for current, the whole idea here is that, hey, if you put more voltage through a circuit, that's going to result in more current. More current just means more light. More resistance means less current. If you increase your denominator, you're just going to have less current. And I can switch back over to the FET applet here and go back to my battery and crank this thing up and be like, hey, more current, or sorry, more voltage, more current, more light. Or we can go and click on the light bulb and we can increase the resistance. And if we increase the resistance, it's almost like squeezing a straw as you're drinking a soda. If you squeeze the straw, you have more resistance or less flow or less light. Okay, so a couple of examples. Here is an example where we have a 12-volt potential difference. So our voltage is 12 volts measured across a load that has a resistance of 60 ohms. What is the current through this load? So if we're looking for current, that'll be voltage divided by resistance, or 12 volts over 60 ohms. Okay, our current in this circuit would be 0.2 amps. Okay, and 0.2 amps, I'm going to switch this to a prefix that we've seen before with millimeters, and that's just 200 milliamps. So I mentioned this because we'll see this in other questions. Either milli or kilo are common prefixes that we use to talk about values in electricity. So 0.2 amps is the same as 200 milliamps. That's how much current would be going through this load. Okay, another one. What's the resistance of a light bulb that has 53 milliamps? So our current is 53 milliamps, okay, which is, milli is moving our decimal place 3 times. 1, 2, 3, so let's put 0.053 amps with a voltage of 150 millivolts. So again, we'll move our decimal place 3 times for the milli. The amount of voltage would be 0.15 volts. Okay, resistance is voltage divided by current. If we rearrange our V equals IR formula, okay, our voltage is 0.15 volts divided by 0.053 amps. Okay, for this we get an answer of 2.83 ohms. Okay. Okay, here is one for you to give a try to. Can answer that on your screen, and just a reminder, this milliamps, that's got to be changed into amps. Can you state the resistance of this load in ohms and in kilo ohms? Okay, some practice problems for you to try. This is sent out as Chapter 9 textbook problems, so we'll have to search through those a little bit to find 3 questions on page 454 and the 3 questions on page 457. Thanks, ladies and gentlemen, and we'll see you again soon.